Hello and welcome back. We're getting really close to the end here, and it's finally time to start talking properly about pointers and their relationship to memory in C. So, for this learning module, we're going to start with some conceptual analogies to pointers before looking at what we've already looked at a little bit before with regards to function arguments using pointers. An important subtopic we'll also cover is sort of the equivalence between pointers and arrays in Cs. And then finally, at the end, we'll start talking about dynamic memory allocation, which is one of the major use cases for having pointers in C and in your programs. So as we saw, going back to our topic on functions, with functions just being called by themselves, you can have no return, or you can take the return value as your output assignment for that function. But that's pretty limited, right? We saw that without using globals or other things like that, you're really limited to one variable you're changing as the output of a function. And one of our other workarounds was this idea of a pointer. We saw it with scanf that our scanf function call looked a little bit different than printf, that the format string had a pretty similar looking syntax, where in this case we're specifying we want three different integers to be parsed as part of the function call. But instead of passing the variable names we printed out, we were using this little ampersand operator in C to specify instead, here are three variable addresses we actually want to overwrite with the results of that scanf call. And that was our first exposure to pointers. And then we saw that using pointers, you can actually pass as many of those addresses as you'd like to a function and effectively get multiple outputs via that passing of those addresses. They're not technically outputs of the function, but it gives you the same result, that as a side effect of running that function, we've not only returned whatever value the function needs to return, and scanf does return a value that we typically don't use that frequently in this course, but you can actually then update those locations in memory and effectively get an equivalent of that many variables being returned by that function. So our current view of memory is still pretty reasonable in terms of we have these bytes corresponding to these variables. Our variable types in C have the different sizes associated with them. So while these addresses may not be strictly correct, we can at least think of it as there being a 4-byte integer A that starts at some address, and then some 4-byte integer B that starts at presumably a consecutive address. And then from that perspective, where we have this view of memory, where it's just an array of bytes, we conceptually kind of combine some of those bytes to correspond to our individual data types. From that perspective, pointers are nothing more than just a special variable type for storing an address in memory. That is all a pointer is. A pointer is an address, or a pointer is a variable that stores an address. I can say that 50 times, and I think you still just have to experience that as you're writing programs, but that is all a pointer is. It is a special variable type for storing an address, presumably an address corresponding to some other variable in memory, although not necessarily. It's just a variable that stores an address. We can indirectly use that to refer to other variables, or we can do other manipulations of those addresses via things like dynamic memory allocations. To print out your pointers, there is a %p format string that you may want to use. There's also, you can just print it out as hex, and you can print it out as a decimal as well. So let's take a look at our kind of first very simple program, I think, that is working with pointers. So here we have our just simple main here that is having an address A and having an integer A and having an integer B, and we're doing a printf, not a scanf here, and we're passing it, instead of the value of A and B, which we didn't actually initialize to anything in this program, we're instead printing out the address of A and the address of B. So in this example, A and B are themselves not pointers. We can get the equivalent of a pointer for A and B by using that ampersand operator. Give me, and when you see that ampersand, think address. Give me the address of A and give me the address of B. And that's actually what's going to get printed out here using that %p flag. It's going to be a location in memory. It's going to be in this case, I think, a 64-bit hexadecimal value that's going to print out. And we can also explicitly declare variables as being pointer variables. So when you see int star c, and the type we're pointing to does matter, as we'll see here. It needs to know, am I pointing to a 4-byte thing or a 1-byte thing or a 64-byte thing? In this case, we're pointing to an integer, and it's a variable that's storing or is intended to eventually store an address corresponding to an integer or potentially array of integers in memory here. This A and B are provided an address via the compiler and the runtime. That's that stack where we store the local variables. So that should have a valid address. If we just declare something as a pointer and don't do anything with it, it's going to be uninitialized. It's not going to have a valid pointer. Fortunately, that %p allows us to visualize that. So we have our A and we have our B. A and B are some reasonably large values in our stack address space here. C is nil or null. It's an uninitialized pointer here. That's not necessarily a bad thing. That could be our intention at this point in the program. If we want that C to correspond to something else, there's a lot of different ways we can do it. So this example here is using dynamic memory allocation. We can instead do C is actually going to be the address of A. A is an int, address of A or ampersand A is an address of that int. C is a pointer meant to store that address. So we should get the same result when we print the C as when we printed the address of A, and we do here. Another approach then instead is to say C is going to correspond maybe to an array of integers. We'll talk about the syntax for dynamic memory allocation, but this is the correct way of doing it. Do a memory allocation of 4 integers and return back a pointer that I can then use later. And that's going to be a different range of memory. It's actually on the lower end of memory. As we'll see, that's where our heap is going to get stored. So again, not to belabor the point too much, but frankly, this is the major point of working with pointers. Pointers are special variables with the intention of storing a location in memory. Ampersand A is one way to get that address of a variable, but we can just separately just specify a pointer variable and either explicitly assign an address or call a function that returns an address, and that is all we're using those pointers for. Here's a somewhat mediocre pointer analogy, but it matches our previous mediocre analogies we've been using this semester, right? We can think of a pointer as being a key, right? I have this key, and on that key it specifies a location in our mailbox, which would correspond to our memory like before, where I can access my data or my mail. So you would use that key, or in our case, the term we use is reference that pointer to open the mailbox 333 for location 333. That's equivalent to referencing the pointer to read data at address 333. And then finally, you get your data. You get your mail inbox 333. That is the data at address 333, which then using that key or using the pointer, you could read or you could modify, you could write. This analogy only goes so far because the pointer itself is also a variable. This key is itself stored in some other mailbox, if we're going with this mailbox analogy here, but it's a special type of variable that's really meant to open other mailboxes. So it's a variable that's intended to reference locations in memory. So because, though, that this variable is itself going to be a variable in memory, you can have a pointer to a pointer, a key to a box that contains a key to another mailbox, and you can keep going. You can have a pointer to a pointer to a pointer. We'll see a couple examples of that. It's where life starts to get a little messy. So this analogy corresponds to our previous sort of locker room or mailbox analogy of understanding memory in general. This is the new addition to it where we have this special variable that really tells you where to look, that tells you that there's something interesting at location 333. That's what we're going to then use to actually determine where our memory is versus just a variable name, where before we had a person's name on the mailbox, and that's how we were accessing mailbox 333. Here's a slightly more awesome, pointer analogy, closer to a map to our data, right? Pointers don't unlock things in memory, right? There's no locking or unlocking of locations in memory. So it's actually closer to a map, right? Our pointer is telling us where we will find valid data. We usually, although in this example we were explicitly printing out the pointer, we usually, unless we're debugging something quite subtle, we usually don't actually care about the actual address. And by care about the actual address, I mean by the 64-bit or 32-bit value, the ones and zeros that are stored in that pointer. We trust the runtime, the compiler, the standard library we're using to return valid pointers for us, and we use those pointers all the time. We don't actually care generally what the location is in memory of those particular pointers. The edge cases where you will start to care is if you're running out of memory, or you really need to place something very specific for an embedded system and you need to have a pointer to a very particular location in memory. But usually otherwise we say we have variables, we can create pointers to those variables, or we can allocate memory using those pointers, and we just trust that the values are valid. We print them out here just because we're curious to see what they look like, but that's the only time you'd ever really look otherwise at that address that is being stored in those pointers. I mentioned this briefly, but this is kind of an important point. Your data types in C are all going to be a different size in terms of the number of bytes that they're storing. And as a language design decision then, each pointer variable is going to then be data type specific. So your int pointers are different than your float pointers, different than your double pointers, different than your custom data structure pointers, as we'll see. Because of that, we do have to be careful when we're creating our pointers and when we're using our pointers. The compiler will get mad at us pretty quickly if we're a little sloppy with our types. Like if we're sloppy with our regular variable types, the same issue happens with our pointers for that reason. So while we have the syntax for our variable declaration, int, float, double, our data type, variable name, we have the same exact syntax for our pointer declaration where we're specifying data type pointer and then the pointer name. Data type star, and the star could go before a space, after the space, but this is a pretty common way to do it. Data type star, that's declaring that we have a variable pointer type here. As we saw in the previous code example, we can explicitly set the pointer to an address using that ampersand operator. And then the other new syntax we have is after we've declared that pointer, we then dereference that pointer. Adding that star again is saying we are following that pointer. We're looking at the treasure map, we're unlocking the mailbox, whatever analogy you want to use. So we both use that star syntax to declare that a variable is a pointer. Now when we want to actually get the location and use that location in memory, read, modify, write that location in memory, we use that star syntax again at that point. That is dereferencing, kind of an ugly term, following the pointer at that point. So in this example here, we've declared a regular int variable. We've declared an int pointer here. We've actually set the pointer to be the address of that original variable we've declared here. By doing a star pointer here, following that pointer, we would actually be updating the memory corresponding to that variable. That's because it's on the left-hand side of our assignment operator here. So we're writing to that location in memory. We're updating that integer. And that's, again, why we need to know what type of pointer it is, whether it's an int pointer or a float pointer. The system needs to know, or the language or the compiler, what have you, needs to know when I follow that pointer, how many bytes am I writing to memory or reading from memory when we're following that pointer. So if this is an int and this is an int pointer, I then know that when I follow that int pointer, I'm going to be updating an int number of bytes at that location in memory. That is dereferencing or following that pointer. So going back to functions here, we can then use those pointer variables as our function arguments to then overwrite the memory locations corresponding to more than just one thing. So this is a function, it's a little swap function that actually has no return results itself, but because it's using pointers as inputs, it can then update memory locations corresponding to, in this case, 2 variables at a time. So we've seen this swap operator a few times when we've been doing sort operations where we've been doing just local swaps. If we wanted to write a function that swapped 2 values without pointers, that's a little tricky in C, right? Because we can only return 1 value. How do we change 2 values in one function? Well, pointers get us around that restriction as we saw in the previous learning module, but now hopefully you understand it a little bit better, right? So we declare in this example an input to this function, basically a pointer to one integer and a pointer to another integer, and they're named accordingly. A pointer, B pointer here. They're both int star. They're both integer pointers. We still need that temp, not a temp pointer, but an integer temp here to store the temporary value so we can swap without overwriting things. And then our syntax looks kind of similar to when we were doing swapping before, except for the pointers, we're dereferencing those pointers. We're following those pointers. So temp, and we can do this in the opposite order, but it's fine in this order. Temp is stored as whatever was in location of memory that B was pointing to. That's now stored as a local variable called temp. We then are following both the B pointer and the A pointer. We're basically overriding whatever B is pointing to by whatever A was pointing to. And then finally, we overwrite whatever A was pointing to with temp. And that would swap whatever A was pointing to with whatever B was pointing to. That gives us our kind of swap result here. Let's take a look at it in practice. So this example just sets 2 variables, x and y, and just prints out before swapping, here's the value of x, here's the value of y. I actually created 2 versions of the function here. One is just you could call it like a buggy swap or a swap without using pointers. Let's look at that function real quick first. So I think it would have been a valid approach to have considered something like this as our swap function, right? I mentioned to you last time, when do you create a new function? Well, when there's this piece of functionality in your code that you see yourself doing over and over again. So a swap function is a reasonable function to write for a certain class of programs. This version just unfortunately wouldn't work, right? It takes as input an integer a and an integer b, and it does that swapping operation. But and I'll have a slide on this as well. If we think about the scope of what's happening in that integer version of it, swap has its own scope and would have its own memory, the stack associated with the implementation of that function swap at runtime. And so while there would be this swapping of a and b inside function swap, that would not correspond to the x and y, and not just because they're named differently, because it's a different memory space. If we'd called this all x and y, it still wouldn't work. This swap is technically swapping, but it's not changing the x and y. So when we call printf the original values, then we call this kind of local swap, we're going to get the same results, and we do. Before swapping, x equals 7, y equals 5, and after swapping, x equals 7, y equals 5. But this pointer approach does then work. So then we call swap pointer. We have to be a little bit careful. Now we're not passing x and y to swap pointer. Swap pointer doesn't expect two integers as input. It expects two integer pointers as input. So we have to provide it with two pointers. Well, we're providing it the pointer to x and the pointer to y here, or the address of x and the address of y here. And it's doing that exact code we had on the slide, where follow the pointer to b and store the result as a temp. Update now whatever b was pointing to with whatever a was pointing to, and then likewise update now whatever a was pointing to with that temp variable we had stored. And that's why that swap, as you can see, actually only happens after we've done that swapping. Maybe a better name for that would be, we're not swapping pointers, we're swapping via pointers is what that function is doing for this example here. So again, that is not a function of the names of the variable here. It has to do with the scope of memory. So we have our main. It has its own memory space here. Our functions have their own memory space here. The reason this all works at all is when we pass those pointer to a and pointer to b, or it was x and y in the example here, the a pointer and the b pointer are in swap pointer's memory space, as is that temp variable, but their address is in memory. So they're storing, this itself is a variable in memory. The key itself is stored in the mailbox somewhere. It's memory all the way down. But then when we actually set the value of that pointer, we're storing an address. And we saw from our examples it wouldn't be 0 and 4. It wouldn't be such nice clean numbers, but we're storing a value in memory. And that value would correspond to wherever the original a and b were in our function main. So consequently, it does work for that reason, right? Our scope is still the same. We haven't made global variables here, but we have these pointer variables that we're setting the actual addresses in memory. And it's kind of a trick with addresses. We're indirectly locating those values for a and b, and we're swapping them via those addresses versus trying to copy the values of a and b and attempting to swap it via some global or some other approach there. I think if this example makes sense, you're in good shape. Because this is not a trivial thing. I want to make that clear. I mean, none of this has been trivial. You've been working on really hard things, throughout this entire class. Pointers are extremely complicated at the end of the day. And so these examples, we start kind of small, kind of work our way up. But in terms of the bugs that you will find in your programs, if it's relating to pointers, those tend to be a lot harder to debug, to track down. And not just in your kind of introductory code, in advanced code bases, in really complicated code bases that hundreds of people have contributed to and looked at, we're still finding pointer-related bugs, pointer-related security vulnerabilities in code that thousands and thousands of hours have been put into, and they're hard. And some would say this ability to do these so-called raw pointers in C as well as in C++ is considered to be a big flaw in the programming language itself. It is certainly what makes C, at least to some degree, harder than some other programming languages that frankly just don't let you do this. But if that previous example, and I would say the example on this slide as well, if you can follow through that example and logically it makes some sort of sense, then as you're working on programs, if you can have that model of memory in your mind, I think you're going to be okay. Yes, your errors are going to look worse. Your programs are going to crash when you have pointer problems. they're not just going to give you a wrong result. You're going to get segmentation faults and memory errors, and things are just going to crash. When that happens, it's a pointer problem. And that's okay because it's just an address that isn't what you think it is or wasn't set the way it should be. And you're just accessing memory that's outside of the valid range for that program. So pointers are hard, but as long as you remember that key fundamental point, that your pointer variables are just corresponding to an address's memory, you're going to be okay. Because otherwise, and you'll see programs where it does get a little bit out of hand, right? Our key is in a mailbox, as in a mailbox that has a key in it that is to another mailbox, etc. And you can do that, right? You can have your pointers to pointers to pointers, and that's what this example is showing here. So we can have an initial integer that gets put in some location in memory. We then can declare an int pointer, int star, that is going to be storing the address of that. So I show that it's kind of a dashed line here because the value stored in here is whatever this address happened to be here. And we can actually then keep going. We can then have an int star star, which I'm pronouncing it that way. It's a pointer to an integer pointer, or a pointer to an integer is a valid way of thinking about that. And syntactically, it's exactly maybe as you would hope or think it would be. So this is just itself just a separate address. Pointers are just addresses that are corresponding to variables in other places in memory. This is an address, and this is a pointer to a pointer. So it would be valid to set this one not to point to the original integer itself, but to point to the pointer to that integer itself. So it is a pointer to a pointer. And syntactically then, we could call scanf, for example, and scanf expects a pointer to an integer if you're doing %d here. So we could either explicitly just pass it the address of my int, like we've been doing all semester, or we'll get the same exact result if we pass in my int pointer, because that is the same as this. It is an address. Or we can actually follow the first pointer for my int pointer pointer, and we get that same exact address. If we were to print out with %p these three things, we'd get the same exact location in memory. If you don't believe me, let's run it here together. The same exact syntax here. My int is a variable in memory. My int pointer is going to be that address corresponding to my int. My int pointer pointer is going to actually be pointing to my int pointer, which we can then follow twice to get back to my int. So with enter 3 integers, we can scanf my int the classic way and get a result. We can then do it again, and we can actually see that it's my int each time that's getting updated. Because whether it's an explicit ampersand address reference, or whether it's a singular pointer where we're just passing in that pointer, or whether it's a multiple pointer or a pointer to a pointer that we're following part of the way, we should get the same exact result. We're updating addresses in memory. So I think if you have that, you're in pretty good shape. But having said that, there's one more point I really do want us to cover just in this video itself, and that's the so-called array pointer equivalence here. Because we saw that our pointer is corresponding to an address in memory. That is what a pointer is storing. We know from our extensive use of them so far in this course, our array variables are also corresponding to a sequential set of addresses in memory, right? When we declare an array of a certain size, we know we're actually allocating that many locations in memory corresponding to that length of the array times the size of each individual element in the array. The syntax here is a little weird, but if we don't know the type of X, we can say we actually then know, although we haven't been using this exact terminology, that the address of a location X of I in this array is equal to the previous location. So X of 4's address is equal to X of 3's address plus however many bytes to store that individual element. And more importantly, that empty syntax where we just use the name of the variable. So if X is declared as an array, just using the variable name X is essentially a pointer, and it's actually not essentially a pointer. It's literally a pointer to the first element of that array. So I refer to array and pointer equivalence, that this is the key point with the word literally bolded here. X, where X is an array. Just using X in your code without any bracket, any integer offsets or whatnot, is the same as that first location's address in memory. That is just part of the spec for C as a programming language. We've been using that a little bit this semester when we've been kind of refactoring some of our functions to do that. So That is the reason when we do scanf with %s, and we've been doing that all semester, we've just been passing to it the name of the character array we wanted to update, the string we wanted to update. We could have, in fact, done this. Instead of if x was a character array, we've been passing x to scanf to override it. We could have done ampersand x of 0. Either would have worked. This is the much more standard approach, I think, because x, where x is an array variable, just referring to x by itself without any squared brackets, is literally a pointer to the first element of the array. Because we know that's what arrays are. Arrays are corresponding to a sequential set of addresses. Just by designing the language, the variable name for an array an array variable, just the name by itself is a pointer to that first element. The only tricky part is when we were working with strings, we didn't have to worry as much about length. For other arrays, we do have to keep track of the length ourselves. So when we have these function calls, as we've seen, it's very common if it's not a string array, we have to pass both the actual array itself as well as usually a secondary length variable to keep track of the elements that we have in our array. We've been doing that all semester. So not all pointers are going to point to arrays. Our previous examples, the pointers were just pointing to one variable of that type, but all arrays have pointers corresponding to them. So x of I is the same as that base pointer plus an I offset and following that pointer. So for all of our functions we've been working on that use arrays, or all of our code that's been using arrays, but it's more clear when we're doing it as a function boundary here, we can rewrite it as an equivalent function with pointers, and the code is identical. There may be some small implementation or optimizations that may happen because compilers can reason more about arrays than they can about pointers, but in terms of the functionality of the code, it's identical. So this dot product example, which does a dot product of two arrays, we pass in one array, two arrays, as well as the length of each array. That code can be refactored and be an equivalent code by instead passing it two pointers. A pointer A, a pointer B, where each pointer is then corresponding to an array. Again, not all pointers point to arrays, but they can. So in this case, this code would have been set up that A would be pointing to an array, B would be pointing to an array, and then we can still use that bracket syntax to indicate that because A pointer and B pointer are pointing to arrays, it is the same. The name of the variable, if it's an array variable, is the same as a pointer to that first element of the variable. It works in both directions. So even though we're passing it as kind of a pointer here to the function, we can still use that bracket syntax, and that's going to give us the offset of I elements into those arrays. Another way to say this, it's going to work exactly as you would hope, I guess, with that syntax here. The array and the pointer arithmetic does exactly what it should do to give you the right offset into that array. So in fact, you can continue to use that empty bracket syntax for pointers to multi-dimensional arrays. We've done that a couple times. The syntax starts to get a little messy. So it's a little bit more of a stylistic point than a hard and fast rule. But while we've been doing this syntax where every dimension has to be set versus as opposed to save for the first dimension of that multi-dimensional array. So this empty bracket syntax is x is a pointer to an array of arrays of size 3. Y is a pointer to an array of arrays of size 4 of arrays of size 3. Using conventional pointers are a lot more common for multi-dimensional arrays. So int star star x pointer is a pointer to an integer, as we saw, or it actually could be a pointer to an array of pointers, each of which then points to an array of integers. We'll probably have to draw that out for that to make sense as we work with multi-dimensional pointers. We don't do a lot of that this semester, but we do a little bit of it, so I do want to make sure we have some reasonable examples associated with it. And finally, although I don't have the code to show for this, it can be definitely a little confusing when working with pointers in C, that sometimes you have to be aware of the size of objects in memory, and other times you don't. But as a language, doing math on the pointers, doing arithmetic on the pointers, actually works exactly how you would hope. You don't actually need to be aware of the size of the object to modify pointers using arithmetic operations. I don't have this code to run to show you, but you can try it yourself. A car pointer is different than an int pointer because we need to know how big each element is. Our car is going to be one byte. Our int's going to be potentially 4 bytes here. So when we run this code and we do int pointer plus plus and car pointer plus plus, in fact, what's going to happen is this int pointer is going to increment by 4 because we're jumping 4 bytes into the future when we do plus plus. car pointer plus plus is going to increment by 1 because we're moving 1 byte ahead of ourselves in memory. Um, that's just something to be aware of, that you can do arithmetic on pointers, and it's actually updating the pointers. It's not just doing integer arithmetic. So it's really what it's doing is int pointer plus plus is taking int pointer plus size of whatever that thing was pointing to, plus 4. So that's why it's doing the plus 4 when we do a plus plus operator there. If you're doing like raw arithmetic on pointers, you do of course have to be careful, but it does actually work the way we would hope here. And finally, and this is a critical point that we'll kind of cover two different videos on this here. When doing image processing, just as an illustrative example, or even just those kind of arbitrary examples we have here, we've been trying to keep it kind of safe and saying, let's assume that we know the size of all of our arrays before we get started. So we didn't have to worry about the so-called dynamic memory allocation. This approach has a potential workaround where we do a scanf and we say, declare a variable array of that size n by n. That does work in some scenarios, but actually doesn't work in a lot of other scenarios, so we can't really rely on that all the time. But this is so-called static memory allocation, right? Where the compiler is able to determine how big our arrays are going to need to be at compile time. We've been relying on it all semester long. We've been okay with it. That is one potential approach. Another potential approach is to say, well, we have this array that we want to process, and we don't know how big it's going to be at runtime, but maybe we potentially know how big it could possibly be at runtime. That it's going to be 1024 by 1024 or smaller. And in that sense, static memory allocation still works for us. It's a bit of a hack. It's a bit of a workaround. That with static memory allocation, we're saying, well, I don't know how big it's going to be necessarily, but I'm going to allocate more than enough memory and then just use a subset of that at runtime. That is a waste of memory, but it's not necessarily a terrible approach. When in doubt, that approach will work. That is in contrast to the static memory allocation to the so-called dynamic memory allocation scheme, in which the addresses or the range of memory that is going to correspond to our array variable is determined while the application is running. And not just at a single point in time, but potentially growing and shrinking over time as well. So there's going to be a function that allows us to allocate a set amount of memory. We actually briefly saw it there in the previous code example. There's then going to be a function that's going to allow us to resize that region of memory. And then there's going to be a function that allows us to kind of zero out or return that amount of memory back. In C, it's a little bit more challenging because we do have to work with pointers and these standard library functions to do this via doing static memory allocation. But once we've done the dynamic memory allocation, working with that variable is the same as it was before. Our array syntax all works, for loops and things like that. That all still works like it was before. So one of the C standard library functions you're going to become very familiar with is malloc. Stands for dynamic memory allocation or memory allocator, where we do have to first declare our pointer variable. And we're going to call malloc where we're specifying the number of bytes we need allocated. Malloc takes as its only input the number of bytes you want. Do I want 100 bytes? Do I want 400 bytes? Do I want 800 bytes? And then malloc as a prototype for the function has a void pointer associated. We then have to cast it to the type of variable pointer being allocated. You don't technically need to, but you'll get compiler warnings when you don't. So if I have an int star pointer, malloc is going to return a pointer to the newly allocated memory, and we're going to cast it to an int star type to return that. So if we wanted to allocate 15 integers in an array named A, and we have a pointer to that array named A, we could do the following. We declare int star A, we then call malloc, in this case saying I want 60 bytes, and we're going to cast that return value from malloc to an int star and just set that as the result of A. Malloc returns an address, but it's also allocating the memory for us, so we actually have, in this case, 60 bytes to correspond to our 15 pointers. Hard coding it like this is pretty bad practice. On 99% of the systems you're going to run on, an int is 4 bytes, and your code's going to crash and when you're on a system where an int is 8 bytes or something else. It's risky to assume that. So it's much more common as practices to use that size of operator for that purpose. We've used it a couple times just to kind of illustrate very early in the semester how big our variables are. It's useful for this purpose as well, where we can say, I want 15 integers. I assume that's going to return 4, but actually I don't care. 15 integers, so 15 times the size of each individual integer. That should return 60, but again, if it's something more, that's fine as well. Give me 60 bytes, or whatever 15 times the size of integer is in bytes, and store that result as a pointer. Let's leave things here for right now because I think we need to cover this in a bit more depth, and I want to make sure you have a good feel for what we're doing with dynamic memory allocation. Again, I think the point to keep in mind is syntactically pointers are just adding this new kind of asterisk operator that we haven't been using this semester. Conceptually, they are definitely not trivial. This is a hard topic, certainly because debugging and tracing when your pointers aren't behaving properly is not a straightforward thing to do. But I think if we start slow and build our way up, you'll be able to figure it out. So we'll look at dynamic memory allocation in practice. We'll try to build up some more complex data structure using that, and that'll hopefully really help you. I wouldn't yet dive into the programming practices until looking at that second video, because I think it'll be necessary to get a little bit more learning and experience of how to work with these pointers.